This is my contact information in case you have any questions that you think of later. I also have my office location on here. Just a reminder that lectures are going to be recorded and links will be sent to all registered participants by email after our lecture today. And then just a reminder of our course objectives. So last time we talked about the role of statistics in the scientific process, and we talked about rigorous and reproducible science. Another objective is we want to understand the features, strengths, and limitations of descriptive, observational, and experimental studies, which we talked about last time. And then we also want to distinguish between association and causation and understand the roles of chance, bias, and confounding in our evaluation of research. So today we're going to go more into the statistical methods. We laid a good foundation last time talking about the different designs for studies and how that could impact your internal and external validity. And I'm just including some training and educational resources on the slides here, so you can look through those later. So like I said, today we're going to go through statistical methods for visualizing and analyzing data. We're going to give an overview of hypothesis testing, and then we're going to talk about different statistical tests that we can apply to our data. We're going to talk about the student's t-test, analysis of variance, and the chi-square test. And then if we have time, we'll get into some sample size considerations. And then next week, we'll talk about correlation, linear regression, analysis of covariance, logistic regression, and survival analysis. Just to give a recap of what we talked about last time, scientific rigor and reproducibility depend on both repeatability and reproducibility. So repeatable research is if we conduct the same study on the same participants and apply the same methods, we'll get the exact same results. Reproducible research is when we apply a study by taking a different sample from our population and using similar methods, we would get similar results. And we talked about internal validity, which are steps to take to minimize systematic and random error, which will give us the most accurate and precise result. And then we also talked about external validity, which is how likely our results from our sample study can be applied to a real-world population. And then we looked at this pyramid of study design. So not all evidence is created equal, and there are different study designs that will give us more confidence in our results. So randomized controlled trials are the gold standard. For an individual study, this is the best we can do and gives us the most confidence in our results, but it also requires more complexity. And then we also had retrospective and prospective studies that will give us less confidence in our results, but are less complex and easier to conduct. So going into statistical methods, we're gonna go back to this flow chart that we talked about last time. When we are conducting our study, we start with the research hypothesis and we define specific questions. So what questions are we trying to answer? And are these descriptive questions? Are we trying to describe a population, or are they inferential? So are we trying to come up with a conclusion about, say, an effectiveness of a treatment? And then you want to look at what what are you measuring? So we have independent variables, which are what the investigators are manipulating, and then dependent variables, which are what outcomes are we interested in. We can also consider covariates, which are ways that we can adjust for any confounding in our statistical analysis. So as an example, adjusting for age or adjusting for baseline characteristics is an example of covariates. And then we want to understand what are the limitations of our study design. And so once we have a suitable study design, only then can we apply the statistical method. So we also, in this part of the process, we also want to determine the number of observations that we, from the population that we want to take. So this is dependent on, one, the statistical model, but also what resources are available. And from there, we can determine, is the study feasible to conduct? So a study, if a study requires, say, 5,000 patients, that may not be feasible for say, a 3-year study, because we are unlikely to enroll that many patients over that period of time. So it usually takes a lot of collaboration to come up with the statistical analysis plan. So if you involve a statistician, I would recommend involving them very early in the process, probably when you're defining the hypotheses. And that's because the statistical model can only be conducted for certain study designs, and the study designs are what's going to limit what model you're going to, what models we can use. And then finally, after we specify the statistical model, we said what we were going to do, then we're going to actually conduct the study by collecting data, and then finally applying the statistical methods that we pre-specified in our analysis and interpretation. So this brings me to hypothesis testing, which is a core tenet of statistical analysis. So we're going to use this observational study as a kind of a case study to give us an example of hypothesis testing. So we're going to assume that we're a primary care physician and we want to learn about the population of patients that we're seeing. So we want to see if our population of patients have high blood pressure. That is, does their blood pressure put them at risk of a heart attack or stroke? So this is defined by the American Heart Association as having a blood pressure of 130 or greater, or a systolic blood pressure. We're just going to focus on systolic blood pressure for today. So we want to see if the average systolic blood pressure in our population of patients is 130 or greater. So to do this, we're going to collect a random sample of blood pressure measurements from our patients. So we're going to randomly select 100 patients and then measure their blood pressure. So what would be a testable hypothesis in this scenario? So our outcome of interest is the average systolic blood pressure in our population, but this is an unknown quantity. So our question is about this unknown average. So we want to draw a conclusion based on some unknown value. So the null hypothesis generally is a statement of no effect. So in our case, the null hypothesis would be that our population of patients on average is not hypertensive. And then the alternative hypothesis is generally a statement of effect or difference. So in this case, it's that our patients on average do have hypertension. So that is that their systolic blood pressure is greater than 129. So these two hypotheses, you can see, account for all possible values. So either their systolic blood pressure is less than or equal to 129 or it's greater than 129. So there's no other possible scenario that we can observe. So these are just testable assumptions. Here we're attempting to model reality based on these testable assumptions. So we can test whether the alternative hypothesis is reasonable in our population, and we do this through a random sample. So then we can proceed by taking a random sample of 100 patients and measuring their systolic blood pressure. Then we can calculate the average systolic blood pressure based on the sample of patients. And then we can look to see if that average is what we would expect to see if these patients were drawn from a population where their average systolic blood pressure is not greater than 129. So then once we determine that, we can draw some conclusion based on this. But there are two possible sources of error that we can make here. And this is assuming that our sample is representative of our population and that our study is well designed. So this is our sampling error. So there are two errors that we can make. Type 1 error is when also called a false positive finding. So in this case, it would be that the true average is less than or equal to 129, but our data tells us otherwise. This is sometimes referred to as the significance level. And a common threshold for alpha, or the type 1 error rate, is 5%. You would often see this in the literature. So there's another type of error, the type 2 error, which is a false negative finding. So this would occur in this scenario when the true average is greater than 129, but our data tells us otherwise. And a common threshold usually for this type 2 error is about 10 or 20%. So what type of error we make depends on the conclusion and the truth. So type 2 error is related to the power. So you may have heard that term. So beta, or the type 2 error rate, is 10%, then we would have 90% power in our study. If beta is 20%, we would have 80% power. So we're gonna first focus on the type 1 error rate and how we know that for a particular study. So I mentioned last time the idea of a sampling distribution, and this is related to sampling variation. So as a reminder from last time, sampling variation means that a sample, when drawn from a population, is not going to perfectly reflect what the truth is in that population. So for example, let's assume that this figure here represents the population systolic blood pressure. You may recognize this as a normal distribution. So along the x-axis here, we have values of systolic blood pressure that could be seen in an individual patient in a clinical population. And then on the y-axis is the probability of observing that systolic blood pressure in the population. So from this graph, we can see that most of our population will have a systolic blood pressure close to 130. So this means that if you randomly sample, or you randomly pick one patient, one individual patient, they would have a high probability of their systolic blood pressure being close to 130. So it's less likely that this individual patient would have a systolic blood pressure around 180, where it drops off at the tails here. And it's also less likely that the individual patient will have a systolic blood pressure around 180, so much higher than the average of the population. So one individual patient will have a high probability of having a systolic blood pressure somewhere between around 110 and 150. So in addition to the mean, we're also concerned with how the systolic blood pressure varies across the population. So this is the population standard deviation, which is basically the average deviation from the mean of the population. So the mean can be visualized by the peak in this curve. So the mean here is 130. And then the standard deviation in a normal distribution can be visualized by where the curve changes from concave to convex. So where it looks like a hump and then it drops back down, that's around where the standard deviation is. So here in this population, the systolic blood pressure mean is 130 and the standard deviation is 20. So a random sample from this population of 100 patients, we could observe an average systolic blood pressure of 129. Another possibility is we could observe an average of 135, 123, 127. These are all different possibilities of the average systolic blood pressure that we can observe within a sample of 100 patients from this population. So the only thing changing between these studies is how or what patients we're sampling from the population. So we're always taking 100 patients, but those patients are always going to be different. And so this is referred to as the sampling variation. So statisticians have created a framework by which we can know the kinds of estimates that we are likely to observe from some particular type of study. So here is what we refer to as the sampling distribution of X bar being the observed average systolic blood pressure in the sample. This is when the estimate is observed from 100 randomly selected patients. So note that this is not the systolic blood pressure for an individual. It's the systolic blood pressure for the average systolic blood pressure from a sample of 100 patients rather than one individual patient. So this curve can be interpreted the same way as the previous curve, except this time, rather than telling me the probability that an individual patient will have a certain systolic blood pressure, this is telling me what the probability is of a certain average systolic blood pressure from a random sample of 100 patients. So this curve tells me that we're most likely to observe an estimate of the average systolic blood pressure close to 130, similar to the last one. And then we also, rather than the population standard deviation, this curve is based on what's called the standard error. So the standard error here describes how the average systolic blood pressures vary. The average systolic blood pressures from a random sample of 100 patients will vary versus the last plot, which showed the average, how the average or the standard deviation in the previous plot describes the standard deviation or how the individual systolic blood pressures will vary. So the standard error we would like to be as small as possible. So we want this value to be sufficiently small so that we can properly control for type 1 and type 2 error. So we can do this with a sample size calculation. Assume that these are two sampling distributions. One based on the null hypothesis, which is that the mean is equal to 129, and against some alternative hypothesis. So some hypothesis where we could have a mean of around 140. So which distribution is a more reasonable explanation if we observe an average systolic blood pressure of 129? It's probably most likely from this sampling distribution from the null hypothesis. And what distribution is more reasonable if we observe an X bar of 142? It's probably more likely from the alternative hypothesis. But what if we observe an average systolic blood pressure of 135 from our sample of 100 patients? This is a little less straightforward. It's not as obvious from this figure which hypothesis about our population is true. So let's say that we observe an average systolic blood pressure of 135. So we want to know, is 135 large enough to conclude that the true mean of 129 is not likely? So the way that we can make this decision is through a test statistic. So a test statistic quantifies the evidence in some standard format and allows you to easily quantify how different the data is that you observed, how different that is from what you would expect under the null hypothesis. So the numerator is going to be, in this case, the difference between the average that we observed, so 135, and then the minus the population mean under the null hypothesis, which is 129. And then the denominator is some measure of sampling variability or the noise in the data. So here it's going to be the standard error of X bar. So in this case, our statistic here, our test statistic here, T, is going to be 135 minus 129 divided by the standard error, which is 20 over the square root of 100. And this gives us a T statistic of 3. So this means that the observed standard deviation is about, or the observed, our observed average is about 3 standard deviations away from what we would expect to observe if the null hypothesis was true. So this value can also be expressed in terms of the p-value. So this p-value is how many possible studies that we can conduct in 100 randomly selected patients would produce a result at least this unexpected. So here the p-value is 0.00513. So this means that there's a less than 1% chance that we would observe this average systolic blood pressure if the null hypothesis was true. So the chances that this sample is inaccurately depicting this elevated systolic blood pressure are approximately 0.5%. So we're pretty comfortable here rejecting H0. So we're pretty comfortable concluding that it's more likely that our patients are hypertensive versus not hypertensive. So to recap, we were interested in drawing some conclusion about our population based on a random sample of 100 patients from our population. So first we set up hypotheses. So that is the null hypothesis is that the population mean is less than or equal to 129 versus the alternative that the population mean is greater than 129. And then we gather the data and come up with an estimate of this unknown average systolic blood pressure. And from this, we can calculate a test statistic and the p-value. So before we run an experiment, we need to determine what risk of a false positive finding we're going to be comfortable with. So a common criteria for this is alpha equals 0.05. And this means that we're okay with being wrong, or we're okay with a false positive finding, as long as it's no more than 5% of the time. So again, when we interpret the p-value, or when we interpret a test statistic, we're operating under the assumption that the random sample that we've taken from the population is representative of that population. So this internal and external validity are very important with this. So in order to properly interpret the p-value, we need to ensure that our we have internal validity in our study. So we need to know what potential sources of bias exist in this study and what is the impact of sampling error on that finding. We also want to think about external validity, and here we want to know, is this particular sample of patients from the population representative of that population? And then is this study setting or context able to translate beyond this study? So we do all this through the design of the study and possibly through the statistical analysis by making adjustments to our statistical model. In reality, especially in observational studies, true random samples are actually very difficult to obtain, especially in clinical research when we're dealing with people. So oftentimes these are convenient samples rather than random. So this is why we usually create a table 1 or a summary of the baseline characteristics and demographics of a table. So that way, anyone reading the results of your study can come up with some idea of how representative your sample is from the population. So this allows us to assess both the external and internal validity of a study. We also want to be clear when we're drafting our results. We want to be clear with how the patients were selected, because again, a random sample is not really feasible, especially in observational studies. So we want to be sure to clearly lay out what the inclusion and exclusion criteria is, and also how the measurements were taken, so that we can make a proper assessment of the internal and external validity, because there's always going to be some issue in that area. But the question is, could these threats to internal or external validity actually change the conclusions of the study? This brings me to the concept of a confounding variable. So confounding variation is caused by variables that are outside of our control, that can distort the perception or distort our perception of the relationship between the exposure and the outcome variable. So by definition, a confounder is a variable that influences both the dependent variable and the independent variable, which can cause a spurious exposure outcome association. So a classic example of this is we can find some correlation between ice cream consumption and violence, and that's because in the summer, more people come out, more people are eating ice cream, but also because more people are out, there's also more criminal activity or violence, but there's not actually any causal relationship between eating ice cream and committing a crime. So in a prospective study, it's very difficult to screen and recruit homogeneous subjects, so subjects with similar backgrounds and prognostic or risk factors. So this means that the comparison group might not be composed of a similar group of subjects. So the way that we can control this is through randomization in a randomized controlled trial. But this is a problem that arises in retrospective research studies where we're not able to control for all these unknown sources of variation. Going back to our example, our goal here is to try to minimize the effect of sampling error on our analysis. So if we have some idea of what the population standard deviation is, we can determine what the standard error will be at different sample sizes. So this can allow us to select a sample size that will give us some adequate control over the sampling error. So in this case, if we assume that the systolic blood pressure standard deviation in the population is 20, which oftentimes this is based on some literature that has already been published. So we have some estimate. We obviously can't ever know what the true population standard deviation is, but we can have some idea of what it is. So this allows us to see, from here we can calculate what the standard error would be given different sizes of the random sample. So why is this important? So at smaller sample sizes, we end up with a much larger standard error. So for example, in this study, if we had a random sample of 10, our sampling distribution would look more like this. So we have a lot more uncertainty in what we would expect to see. So we're likely to see a much wider range of averages from our random sample. So that would, if we conducted a similar study, but in a population of 10, we would observe a type 1 error rate of around 11.5%. So you can see how this, the smaller sample size gives us less power to find or detect some difference or conclude that the null hypothesis or to reject the null hypothesis. So we're less likely to reject the null hypothesis, even if the null hypothesis is true when we have a smaller sample. So moving on to statistical tests. So the statistical test that we just conducted is called a one-sample t-test, which this allows us to come up with some description of our population. So it's usually used, like in this example, to find if our population mean deviates from some expected population mean. But there's different tests based on different study designs and different research questions. So when you're coming up with or determining which statistical test you want to use, you want to think about what is your research question and then what data will be produced from conducting this study. So what are your predictor variables, covariates, prognostic factors, treatment or exposure, versus your dependent variables, which are your outcome variables. And you want to know if these are nominal, so if they're categorical variables, if they're ordinal, so there's some type of ordering to them, or if they're continuous, like in our blood pressure example. So you also want to look at how many samples are you comparing. So are you comparing a placebo group to an active drug group, or are you do you have some control, or are you only looking at one sample of patients? So how many samples? So this is either in our previous example, we had one sample, so we had one sample of 100 patients. but maybe we want to compare the blood pressure of our patient population to the patient population of some other primary care doctor. In that case, we would need 2 samples. And then you also want to consider how many subjects are in your study, because the statistical tests that you use will also determine all statistical tests are based on some assumption about that population. So if your sample size is too small to use a particular test, you may need to consider other statistical tests, or you may conclude that your study can only be a descriptive description of the population rather than an inferential study. We looked at the one sample t-test. There's also the student's t-test, which allows us to compare the means between 2 different groups. This is appropriate for continuous outcome data. So as an example, our average LDL cholesterol levels for patients treated with one treatment A versus those treated with some other treatment B. So this is used with continuous outcome data when we have 2 groups. The chi-squared test is also used when we have 2 groups, the chi-squared test is often used when there's 2 groups. It can also be used if there's more than 2 groups. And this is appropriate for categorical outcome variable. So as an example, if our research question was, are the percentages of people developing a disease or those at risk of a disease the same in the exposed group versus the unexposed group? So here the outcome variable is the people with the disease versus not. And so this is a categorical outcome. So these both account for 2 sources of variation. So any statistical test that you use is going to, when looking at 2 groups, is going to account for both sources of variation attributable to treatment, and then also sources of variation attributable to our sampling error. So here's a simple example of a 2 sample t-test or a student's t-test. So suppose we're interested in gathering evidence about the effectiveness of 2 competing therapies in reducing LDL cholesterol to healthy levels. So LDL cholesterol is a continuous outcome, so it can take values like 140.1 or 137.9, as opposed to some categorical outcome like sex, where we tend to describe for a group using means. So our interest here is deciding whether these 2 treatments result in equivalent LDL cholesterol levels on average, or if they produce different average LDL cholesterols in patients. So this hypothesis test allows us to select between one of these 2 therapies, or one of these 2 theories or hypotheses using generated data from our study. So this is a hypothesis of difference, which is known as the alternative hypothesis. So our null hypothesis here is that the average LDL cholesterol is the same between 2 therapies versus the alternative, which is that they're different. So again, here we're attempting to model some reality that's unknown in our population. And these hypotheses are really just testable assumptions. Once the testable hypotheses have been constructed, we proceed by assuming that the null hypothesis is true when we calculate our test statistic. After we collect the data, we have to determine whether what we observed from a study is what we would expect to have observed if the null hypothesis is true, or does our data provide evidence of no treatment effect. So if the truth is that there is no effective treatment, then the patient's LDL cholesterol will differ simply as a function of the individual patient differences. And we would expect the means from the two groups to be very similar. So if the truth is that there is an effect of this treatment, then the patient's LDL cholesterol levels will still differ as a function of their individual patient differences. But patients treated with treatment A will differ from patients treated with treatment B because A would have a different impact on the cholesterol levels than B. So we would expect in this situation, or if the alternative is true, that we would expect to see two different sample means from our sample. Remember that there's always a chance, even in a very well-designed study, that we end up with a sample that is not reflective of our population. So sampling variability is always a risk in a study. And so even though we would expect if the null hypothesis is true, we would expect the sample means to be similar. There is still a chance that the sample means would be different. And then similarly, if the alternative hypothesis is true, there's always going to be a chance that we observed similar sample means that make it look like the null is true. So this is due to sampling variability, and this is related to the type 1 error rate, which is the probability that we observe a false positive finding, or that we observe different sample means even when the null hypothesis is true. And then the type 2 error rate is the probability of a false negative finding. So again, we're going to look at two different sampling distributions that can be generated based on either the null hypothesis or the alternative. So here, this curve in the solid line represents the sampling distribution of the difference in LDL cholesterol between the two groups if there's no difference in the groups. Whereas this alternative hypothesis represents there's a difference between the LDL cholesterol for groups A and groups B. So if we observe a scenario where the X bar for group A, or the sample mean for group A is 141, and the sample mean for group B is 140, so the difference here would be a difference of 1. So we would expect that this probably comes from a population in which the null hypothesis is true, or that there's no difference between how the treatments affect LDL cholesterol. Whereas if we observe a difference of -15 between the average LDL cholesterol between group A and group B, we would expect that this is probably from the alternative hypothesis, or we would expect this to be drawn from a population where the alternative hypothesis is true. Whereas if we observe a scenario where the average difference between the two groups is around -5, this is not quite as straightforward. So this will necessitate some calculation of a test statistic. So again, as a reminder, a test statistic quantifies the evidence in some standardized format, where the numerator is the difference between what we did observe and what we would have expected to observe given the null hypothesis, or the signal of the difference or the effect, while the denominator is some measure of sampling variability, or the noise. So in our case, in this scenario, we're hypothesizing about the means of the population. So we're going to use a two-sample t-test. There's also the chi-squared test, which if we were hypothesizing about counts or proportions, we would use that. And then there's also the F-test. This is also hypothesizing about means, but this would involve more than two groups. So going back to our example, we're hypothesizing about the means. So the appropriate test statistic here is the two-sample t-test. So our test statistic here is t, which gives us an easy to interpret description of the evidence that this study, that this data collected in the study provides. So in the two obvious cases, the difference in the means of 15 would give us a t statistic of negative 7.5. So here the interpretation is that the difference in the sample means that we observed is actually 7.5 standard deviations below what we would have expected if there was no treatment effect. So here we're assuming that the null hypothesis is true, so that there is no effect. And then we compare that to what we actually observed. And from that, we can make a decision about whether this is likely, given that there's no difference. So a t statistic of negative 7.5 tells us the null hypothesis is not very likely, and we'll probably reject this in favor of the alternative hypothesis. So in another obvious case, the difference in sample means of only one would give us a t statistic of 0.5. So this is interpreted as the difference in sample means that we observed is only 0.5 standard deviations above what we would have expected if there was no treatment effect. So this data is pretty much in agreement with the null. So we will probably fail to reject the null in this case and conclude that there's no evidence of a treatment effect. So in the last case, the difference is not so obvious. So here we observed a t statistic of negative 2.5. So this study produced a difference that is 2.5 standard deviations below what we would expect to get if the null were true. So we want to know, is this difference enough to be considered evidence in favor of a treatment effect? To do this, we need to look back at what risk we were willing to take in making a type 1 error rate or a false rejection. So here, if no relationship actually exists between treatment and LDL cholesterol, what are the chances that we would observe this, or that this t statistic is inaccurately depicting a difference? So recall from the previous lecture that the p-value gives us the chances that the sample was one of the unfortunate few that we know that can be randomly drawn from a population and still give us an inaccurate evidence and result in a false positive finding. So we should decide before we start conducting a study what the risk is that we're willing to accept. So the decision rule that we use here would compare this p-value to what our pre-specified type 1 error rate is. Oftentimes this is 5%. So in this case, the chances are about 1 in 10 that this is a false positive finding. So the chances that this is a conclusion that the treatments are different, given that the treatments are not different, is about 1%. So a little more about the p-value. So the p-value gives us some measure of the risk of our sampling error. but there's also other sources of error that we talked about last time in our experiment. When interpreting the p-value, we want to know, did the investigator exert control over as many extraneous factors as possible? So is our observed treatment effect actually the result of the difference in treatments, or is it the result of some other factor that may be influencing our study? And then was there randomization? So randomization, again, controls for unknown sources of variation. So this gives us more confidence that the p-value is valid. Was there an adequate control group? Was there blinding involved? Were the outcome measures objective, or is there some measurement error involved in that? Was the sample size adequate? And was the sample size estimated based on some power analysis for the hypothesis? So it's if all these things are true, it's reasonable to conclude that the only sources of variation in the study outcome are the treatment and the sampling error. So here the p-value is a valid measure of the risk of sampling error. But if there are other sources of error in a study, we need to account for that when we're interpreting the p-value. So we're going to go through another example. So like I said before, the two-sample t-test is used when we're interested in drawing conclusions about a continuous outcome variable. But when we have a categorical outcome variable, we use what's called a chi-squared test, which here we have both a categorical independent variable and a categorical dependent variable. So this is an example of a study that was conducted with SEER data, or surveillance epidemiology, and results data, which is publicly available and which collects cancer incidence, prevalence, and survival data in the US. So this data set is large enough to meet the assumptions of the chi-squared test, and so we'll use that for this study. So the investigators are interested in examining a relationship between cardiovascular death, which is the dependent variable, and whether or not the patient had surgery on the primary site. So that's the independent variable. So the comparison groups are based on the surgery status, and then the outcome, which here is death, is the categorical. So here the chi-squared test compares the observed versus expected frequencies of cardiovascular death between the surgery group and the non-surgery group. So our hypothesis here is that the risk of death between the two groups, surgery versus no surgery, is the same. And then our alternative hypothesis is that the probability of cardiovascular death between two groups is different. So in this study, a p-value was observed that's less than 0.001. So this p-value provides an estimate of the role in the sampling error that was obtained in this study. So since the study was observational, we know that there's a high risk of bias. The results should be considered hypothesis generating. So when you're conducting an observational research study, you oftentimes in the discussion of a research paper, you would see what are the limitations of a study. And it's important to point this out so that the readers can get an accurate idea of how well or how valid the p-value represents the actual sampling variability in your data versus other confounding factors. Like I said before, this is the chi-squared test. Here we're interested in comparing the frequencies or the proportions between two groups, whereas previously we showed an example of a two-sample students t-test where we were comparing the means of the two groups. So what about when we want to make inferences on more than two groups? To give an example, we are going to start with the research question related to smoking cessation. So we want to know, is therapy, in addition to education, better than education alone in getting smokers to quit? And if so, which one is more effective? So here, our independent variable is therapy, or is the therapy that they receive. So A is literature, so the patients were just given some literature to give them more information about how to quit. Treatment B is behavioral therapy, and then treatment C is pharmaceutical therapy. And then our dependent variable here is the change in packs smoked per day after 6 months of therapy. So here our outcome variable is a continuous measurement since it's the change in the number of packs smoked per day. So the outcome is continuous, but here we have 3 groups, so we can't use a 2-sample t-test. So what the approach that we'll use is we're gonna use what's called an analysis of variance, or an ANOVA. So our hypotheses here are, we have the null hypothesis that the average change in packs per day is are equal for all 3 groups. So that is that there's no difference in the effect of therapy between the 3 treatments, versus the alternative hypothesis that there is at least one of the means is different. So here we're not identifying which treatment is the best. We just want to know if there's some difference somewhere in the treatments. So oftentimes we might be tempted to conduct all pairwise comparisons using t-tests. So we might break this down into 3 tests, one comparing group A to group B, one comparing group B to group C, and one comparing group A to group C. But the problem here is that every time we run a statistical test, we have some chance of making a type 1 error. So that is, we have some possibility of observing a false positive finding. And so when we do 3 multiple tests, this error rate adds up. So every time we conduct a test, we're increasing the chance that we'll make at least one false positive. We'll obtain at least one false positive finding. So while pairwise t-tests are often tempting, we need to be cautious because this is where methods like ANOVA and multiple comparison corrections can allow us to better control for that type 1 error rate. In this case, to address the issue of multiple comparisons, we're going to conduct an ANOVA test or an analysis of variance. So this is designed to compare the mean response across 2 or more groups, which is defined by some categorical factor. So in this case, it's the type of therapy that the patients received. So an advantage of this ANOVA is that it tests for an overall difference in the means without increasing the type 1 error rate. So this is unlike doing multiple 2-sample t-tests. One disadvantage of this ANOVA is that it can only tell us that some difference exists between the therapy. It can't tell us where that difference exists. So it can't tell us, it can tell us that there is a difference in the treatment, but it can't tell us which treatment is the best out of the three. So oftentimes if an ANOVA test result is significant, we would follow up with some post hoc comparison between the groups to determine which one is the best among the three. So this approach keeps our analysis statistically sound while still allowing us to explore the meaningful differences between the therapies. Similar to the other tests that we looked at, the ANOVA test breaks down the response variable into two parts. That's the variation attributable to the treatment, and then the variation attributable to sampling error. So this is usually involves subject characteristics or some other source of variation that we haven't accounted for in the study. Then we conduct a comparison between these two sources of variation with using a ratio, which here is the F statistic. So this is comparing the mean squared treatment error in the numerator, which is the variation or the estimated variation in the treatment means over the mean squared error, which is the variation within each treatment. So if the variation within groups is just as large or larger, then the treatment likely didn't make some meaningful difference. And so this ratio, or the F statistic here, is the foundation for the ANOVA test. Why are we looking at, our hypothesis is related to the means, so why are we looking at the variance rather than the means? Well, the ANOVA test breaks down the mean square, which is the excess variation. So this is the average difference in the observations from the mean. So this is a variance, but it's looking at how much our observations deviate from some mean. So we're still looking at the mean, which is still a component of the variance calculation. And then we're looking at also the within group mean squared error, which is the natural variation or the natural average that the subject responses deviate from the within group mean. So let's take a look at 3 different scenarios and talk about what these may tell us. So the observed difference between them is how the group medians and spreads differ. So in the first scenario here on the top, we can see that the medians are clearly different across the 3 groups. So group 1 is lower, group 3 is the highest, and then group 2 is in between. In the second scenario, we can also see that the medians are different between the 3 groups. But here, there's also more within group variability. So especially in group 1, the spread of the data is a lot larger than in the first scenario. And same with group 3. And then we can also see group 2 has some outliers. So the variation is a little higher as well in group 2. And then in the third scenario, all 3 groups have similar medians and similar spreads, which suggests that there's little to no difference. So which one is more likely to show a statistically significant result? Well, the first scenario is a strong candidate. The differences in medians are pretty clear and consistent, which increases the likelihood that the ANOVA will detect some difference in the population means. In contrast, the second scenario has a lot more noise. So even though the means are just as different as in the first scenario, there's a lot more within group differences, or the variation within the groups is a lot higher. So this high variability within the groups makes it harder for us to detect some between group difference. And then finally, the third scenario shows no meaningful difference at all, so we wouldn't expect a significant result here. To recap, in the first scenario, we would expect some significant difference, whereas in the other two we wouldn't. Going back to the F statistic, let's consider two different cases. So case A, in case A, suppose that all the sample means are exactly the same. So what would be the value of the numerator that we would expect in the F statistic? So in this case, we would expect the numerator of this of the F statistic, which captures the between group variation, to be 0, because there's no difference in the means of the three groups. So here the F statistic itself would also be 0 or very close to it. So in case B, let's suppose that the sample means are spread out and very different. So this means that there's a lot of variation between the two groups, or the three groups, suggesting some possible treatment effect. So the numerator of this F statistic would be much larger than in case A. And if the within group variation between these two cases is the same, we would expect case B to give us a much larger F statistic, which would increase the chances of rejecting a null hypothesis. What possible values could the F statistic take on? Well, first, the F statistic is always at least 0 or positive, so it can't be negative, and this is because it's based on the ratio of two variances, which also can't be negative. So if the group means are very similar, we would expect that the between group variance would be small, and the test statistic would be close to 1 or less than 1. So this suggests that there's no strong evidence of a difference between the groups. On the other hand, if the group means are very different, but the between group variance will be very large compared to the within group variance. So here the F statistic would be much larger, which would increase the chances of us rejecting the null hypothesis. So looking at the results of this, we can see that this case study led us to an F statistic of 22.64, which gives us a very small p-value. So in this case, we're going to reject the null hypothesis that the treatment means between the three treatments are the same. So this suggests that there's sufficient evidence to conclude that the mean number of cigarettes smoked per day differs between the three types of therapy. Like I mentioned, there's one limitation of the ANOVA test, is that we don't actually know where this difference lies. So we know that there's a difference, we just don't know what the difference is. So that's why we would often conduct a post hoc test if we find statistically significant difference. So in this case, we use Tukey's HSD, which is honestly significant difference. I'm not going to go into this in detail. This is just to give an example of a type of post hoc test. So we know that there's a significant difference overall, and this test allows us to know where that difference is. So what this does is it tests all pairwise comparisons while also controlling for the type 1 error rate. So it ensures that our type 1 error rate is non-inflated due to the multiple comparisons that I talked about earlier. So here, so this B minus A is 1.62, which suggests that the behavioral therapy performed better than just education. C minus A is 1.7, which suggests that the pharmaceutical therapy also performed better than just education. And then C minus D is 0.58, which suggests that the pharmaceutical therapy also performed better than the behavioral therapy. So here we would conclude that because all the p-values are significant, we can conclude that adding either behavioral therapy or pharmaceutical therapy to education results on average in greater decreases in pack smoke per day when compared to just education. And we can also conclude that pharmaceutical therapy showed the most benefit among the two experimental interventions. So this is because the values of these differences are positive for these two differences and this difference. So to summarize, we looked at some inferences on mean. So we looked at the 2-sample t-test when we have 2 independent groups. We also looked at the 1-sample t-test where we only have 1 group that we want to make an inference about. When we have more than 2 independent groups, we want to use an ANOVA. One thing to note here is that be sure when you're conducting a statistical test that you're aware of what the assumptions are of that test. So in the ANOVA and the 2-sample t-test, the assumptions are that our response variable is approximately normal, and that the variances are approximately equal. So it's important to test that those assumptions are true before conducting the statistical test. And if they're not true, you may want to consider some alternative like a non-parametric test that would be more valid in scenarios where these assumptions are violated. So I want to go more into inferences on proportions. So we looked at a chi-squared test of independence where we had an independent variable and a dependent variable with two different groups. So I want to give an example also of a case where we have 2 groups in our independent variable or the treatment, but then we have 4 groups in our dependent variable. So to give an example, we're looking at a study where our independent variable is some treatment, and then the tumor response is our outcome variable. So our outcome variable can vary. It could be either a complete tumor response, partial response, stable response, or a failure. So here we're looking at whether 2 categorical variables are independent of another using a chi-squared test of independence. So this is similar to the chi-squared test that we conducted previously. Like I said, you want to test the assumptions. An assumption of the chi-squared test is that this no cell sample size is less than 5. So the cells in this case are the counts within each of these cells. So there were 32 patients who were received treatment A and had a complete response. So that meets our assumption. And then we want to make sure that all those counts are not less than 5. If any of them are less than 5, the Fisher's exact test is more appropriate. But here, because this meets the assumptions, we're going to go through the chi-squared test. In our process, we want to first identify our hypotheses. So our null hypothesis here is that the response is independent of treatment. So that is the response rates are the same within each treatment. And then our alternative is that the response is not independent of treatment. So that means that there's some difference in response rates between the two treatments. So to evaluate this, like in all of our previous examples, we calculate a test statistic. So does it appear that this type of sample could have come from a population where the rates of the response are the same frequency within each treatment? So to do this, we would calculate the chi-squared statistic where we take the sum of whatever the observed treatment is and subtract the expected or the observed count, subtract the expected count, which is what we would expect to see under the null hypothesis, and then divide by that expected count. And so if we take the sum of this, that would give us our chi-squared test statistic. So this is probably an easier way to visualize what the counts are between each of the two groups. So we can see that it looks like there appears to be a difference between the response rates between group A and group B, particularly in the partial response group. So in group B, we had a partial response rate of 32.5%, and in group A, we had a partial response rate of 43%. So just looking at this plot, it looks like there's probably going to be some difference, or we're probably going to reject the null hypothesis. But to test this assumption, we need to calculate our test statistic. So again, our test statistic is based on both the observed counts as well as the counts that we would expect to see if the null hypothesis was true, or if there was no difference in response rates between the treatment groups. So here we observe a test statistic of 7.9, which if we calculate the p-value based on that, we have a p-value of 0.029. And so our conclusion would be to reject the null hypothesis and conclude that there is sufficient evidence that the response differ by treatment. In summary, inferences on proportions are often done using the chi-squared test, although this is based on the assumption that there's at least five counts within each cell. So if we don't meet those assumptions, then we'll use what's called a Fisher's exact test. So this test concerns some categorical outcome when there are two or more independent groups. And again, as always, you'll need to test the assumptions before conducting a chi-squared test. So I'm going to briefly go through sample size estimation. So I mentioned this before, that when we're designing a study, we need to make sure that we have enough, we're collecting enough data that we can properly control for our sampling error. And to do this, we need to ensure that we have enough subjects to properly control for that sampling error, because recall that sampling error is based on both the standard deviation as well as the actual sample size. So the higher the sample size, the smaller your sampling error is, or the smaller your standard error is. And the larger or the smaller the sample size, the larger your standard error is going to be. When designing a study, it's important to pick a size of study that both controls for that sampling error, but also doesn't waste resources. So statistical methods can be used to ensure that you're recruiting enough subjects to meet the trial's principal scientific objectives, but not recruiting so many subjects. So you want to recruit the minimum number of subjects, accounting for dropout rates that will meet the trial's objective. So other considerations may include the availability of patients. So this is a part of what goes into determining a sample size. Part of it's statistical, but also you need to look at the patient pool that you're drawing from to see if it's even feasible to recruit as many subjects as you need. And then also the resources involved with recruiting more subjects and the ethical need to prevent extra patients from receiving some inferior treatment if we find that that treatment is not as effective as the comparator. So basically, we want to recruit the minimum number of subjects required to meet our scientific objective, but no more than that. When looking at when determining the size of a clinical trial, you want to determine whether your trial is an estimation trial, which involves coming up with some estimate or some confidence interval estimate to describe some outcome of interest. Or is there a hypothesis test? Is it an inferential test to try to detect some difference between competing treatments? So when calculating a sample size for a clinical trial, we need to, one, ensure that we're controlling properly for a type 1 error rate, while also giving us some minimally acceptable power. So power, again, is 1 minus beta, where beta is the type 2 error rate. So we want to make sure that we're properly controlling for the false positive rate as well as the false negative rate. And we want to, another input into a sample size calculation is some clinically meaningful difference. So this is often used, we often use delta to represent this clinically meaningful difference. So depending on the nature of our outcome, we want to choose a level of significance, and then also an outcome that can be estimated within some margin of error, given some sample size. To give an example of a sample size calculation where we want to detect some difference between two continuous outcomes, we'll look at a study where the primary objective is, does some treatment A change the outcome of the outcome W? In this case, W is a continuous variable, for example, HbA1c. So subjects are then randomized equally to one of two groups, either treatment A or the placebo. And our analysis will involve a comparison of the mean response of subjects on treatment A to those on the placebo using a two-sided t-test. And we want to set a level of significance of alpha equal to 0.05. Here we need some either estimate or some level that we expect the results to be given the two treatments. So if we expect the results under a placebo to be a mean response of 10, we want to ensure that we're recruiting enough subjects to detect, to be able to determine if treatment A changes the response by 10%. So we need to do a little bit of math oftentimes to determine this. We need to look at the literature, what have other studies seen, and then as well as what do we expect or what would be a clinically meaningful difference. So if the real difference in response rates between the two treatments is at least 10%, we want to detect a difference that is statistically significant. So a 10% difference, in this case, if the mean response under the placebo is 10, we would want to observe a mean response of at least 11 or an increase of 1, or at least a 9, or at most 9, or a decrease of 1, assuming that the mean response under placebo is 10. So we would also want to consider the probability of detecting this difference. We want this probability of detecting this difference to be no less than 80%. So we want to ensure 80% power to detect some difference given that we observe some 10% difference. So our hypotheses in this case are going to be the null hypothesis that the two means are equal versus the alternative that they're not equal. And then we set a significance level of 0.05, and then a power of 0.8, and then a delta or an expected effect of 1. So for continuous outcomes, we need to determine what difference would be clinically meaningful, but we want to specify this in the form of an effect size. So as an example, going back to our example, Cohen's D is an effect size measure that is calculated as the difference in the means divided by the standard deviation. Here, because we have two groups, we use a pooled estimate of the standard deviation. So oftentimes this is calculated used by pooling the measurements between the two groups and then estimating the standard deviation of that. This pooled standard deviation is unknown, but oftentimes we'll need some idea of what we expect it to be. So this either comes from preliminary data from a pilot study, for example, or by looking in the literature to see if there's any estimate of this, or some estimate of some similar measure. We need some way to have some estimate of the standard deviation. Otherwise, we can also use Cohen's d if we don't have that to estimate an effect size. So Cohen's d is directly related to the differences in means and is inversely related to the variability in the sample size. So as the difference in means increases, Cohen's d will increase, and then as n or our sample size increases, Cohen's d decreases, and then as this standard deviation increases, Cohen's d decreases. So the terms small, medium, and large effects are often relative to the, are often based on this Cohen's d measure, and should be based on, or theirs are often relative and should be based on the specific context. But a good rule of thumb here is that 0.2 is often considered a small effect, 0.5 often a medium effect, and then 0.8 as a large effect. So these are all equivalent to about, so d equal to 0.2 is equivalent, means that the difference is equivalent to a standard deviation of 0.2 of the data. So going back to our example, from preliminary data, we have an estimate of the standard deviation of approximately 2.1, which gives us a Cohen's d of 0.476. So there's software that can be used to estimate the power or the sample size. And R, which is an open source software, there's a function that you can use to compute the required sample size. So if we plug that in to our data or to our function in R, we get that we need a sample size of 71 per group, and this is required to obtain the level of power and the significance level that we pre-specified. So if we observe all right, this system is going to restart. Sorry about that, everyone. If you're online, we're having some technical difficulties. We need to get the presentation back up. So I'm working on that now. Okay, so this means that we need a sample size of 71 per group. So if we have at least this much, if we observe a difference of at least 10%, and if our estimate of the variability of the data is accurate, then the test we do would likely produce a p-value of less than 0.05. But if we observe a difference that's smaller than this delta, or if we have underestimated the variability of the data, the test we perform is likely to produce a p-value of greater than 0.05. So going back to another plot of our sampling distribution, so if we have our null, our sampling distribution, if our population was drawn from a population where the null hypothesis is true, we would have this solid line in the middle here, which would represent our sampling distribution. And if we the two minimum possible expectations under some alternative hypothesis are in the dotted lines on the two sides. So we would expect that if we observe some value within these two vertical lines here, we would fail to reject H naught and conclude that there's no difference. And then if we observe some value on either of the two sides of that vertical line, we would reject H naught, either because the value is larger than what we would expect under H naught, or the value is smaller than what we would expect under H naught. So the power here would be the 1 minus beta region that's shown here, and then our significance level, which is alpha, is represented by the sum of the two regions that are where our vertical lines intersect the sampling distribution under H naught. So to recap this, power calculations, oftentimes you'll need some software to calculate this. Here's a link to a web-based tool that can help you calculate both power and sample size, and it also gives you the ability to visualize a relationship between the power and the sample size. So the inputs into a power sample size calculations are we need some estimate of the variability of the data, and we also need some estimate of the effect size. So the effect size is based on both the difference that we would expect as well as the variability. So increasing alpha or would result in an increase in the required sample size to achieve some given power. So the increase in the effect size would also result in a decrease in the required sample size to achieve a given power, because here we need fewer subjects to detect a smaller difference in the sample size. So to summarize what we talked about today and last week, we have our different study designs, and all study designs have different benefits and drawbacks. And with these study designs, we attempt to account for as many sources of variation as possible. And today we looked at how statistical tests can reflect the study design and the data type to produce valid estimates based on the results of our study. Next week, we're going to look at some statistical methods to account for variation. So even in perfect studies, there's a small chance of producing inaccurate evidence. So there's always going to be some source of error, either systematic error or bias, or random error or sampling variability. One way that we can account for this is to account for additional uncontrolled sources of variation using linear regression. Next week, we're going to look at both linear regression and other ways to estimate a correlation between continuous variables. So if you have any questions, feel free to ask them. You can also email me later, and this is your last lecture that you're attending. You can fill out the feedback form. Otherwise, if you're planning on coming next week, you can fill this out after we're done with that. And I just want to mention in these slides, I also included kind of a simple table to determine what statistical tests you can use, and that's included at the end of these slides. So it looks at whether you have an independent variable or what your independent variable type is and what your dependent variable type is. And then I also give some non-parametric tests. And then there's also this little flow chart that you can use to determine what statistical tests you can use. So that's all I have for today. Does anyone have any questions? Okay, I don't see any in the chat. All right, thank you, everyone. Hope to see you next week for our last lecture. Thank you.